Hi guys, welcome back to In Case of Econ Struggles. Today I'm going to start talking about econometrics and simulations. In order to do that, I'm going to talk first about the law of large numbers. So timestamps are below if you would like to jump around, but let's go ahead and get right into it. So before I talk about the law of large numbers specifically, I just want to talk about why simulations can be useful in econometrics, and there are a couple reasons that I can think of, but of course, if you can think of other reasons why simulations are helpful, go ahead and put that in the comment section below. But the reasons that I think they're useful is that one, our computer is pretty fast, and the examples I find are typically easier to understand than doing a bunch of theory. When we do simulations, you know what the true value of the parameters are, and so you could sort of compare, does your simulation get the parameter that you know is supposed to be the true value? And also, it's really easy to tweak and update simulations as you go along. Finally, you don't need any actual data because you're creating the data. You don't have to go out and find observational data. You can just whip it up and state it in a couple minutes, and the results that you get are going to be pretty useful and helpful again for understanding econometrics, but also applied work when you get into sort of doing your own research. So with that being said, let's start talking about the law of large numbers and maybe some general vocab that we're going to use in simulations broadly. Suppose that our goal is to show the law of large numbers, which just means that as n our sample size goes to infinity, our sample mean is going to go to the true population mean mu, so x bar is going to mu as n goes to infinity. And so what we're going to say is that there's a data generating process where the truth here is that, I don't know, maybe the average lifespan of cats is 15 years, so our mu is 15. And so what we need in order to show that the law of large numbers works, we need a bunch of different samples with a bunch of different number of observations in each of those samples. We need to create a sample mean for each of those samples and show that as our sample size gets bigger, as the number of observations within a sample goes to infinity, that our x bar becomes closer and closer and closer to mu. So one thing I just want to review is sample versus population, where again, when we have a population, that's like all the cats on Earth, and so the average lifespan of all cats on Earth is 15 years. But when we're doing statistics, we're not looking at all possible cats. We only have a few cats that we're looking at. Specifically, we have n cats, or our sample size. We're calculating our sample statistic, our sample mean, based off that sample, which is just our average, which is not necessarily going to be equal to our population average. But the law of large numbers says that as that sample size goes to infinity, eventually we are going to measure every possible cat. And so as our sample size gets larger and larger, it should be in the limit that our x bar, that our sample mean, approaches or equals our population mean mu. So now we sort of got the basic idea, and I just want to pose a question of do you think this would work or not? So suppose we're going to create some simulated data sets. They're going to have different number of observations. We'll have a data set with one observation, with 100, with 1 million. We'll just play with the different number of observations that we can have in a sample. And for each data set and each row, I'm going to create this variable x, and that variable x is going to be equal to 15, or the population mean for every single row. And so why or why not would this simulation work? And while the simulation is not going to be a helpful simulation, which you probably guessed, because our x bar is going to be 15 for any sample size. So as our number of observations gets bigger and bigger, well, the sample average is 15 for every single sample. So that's not really going to demonstrate the law of large numbers for us, because it's really going to be the case that, well, even if you had one cat, well, if every cat had exactly 15 years in terms of their lifespan, then there's no variation. You're not showing anything because the sample mean is 15 for every sample. It's also not very realistic because not every cat lives for exactly 15 years. There's some variation in lifespan. And so what we can do is we can add some noise to make this data more realistic and to make our simulation more useful. And so again, if our mu is 15, maybe what I'll do is I'll generate my x's for each sample as this 15 plus some noise. And when I add some noise, one thing that's going to be really important is that I still need it to be the case that when I add this noise, I don't change the mean. And so one way that I can add noise that's pretty helpful is I can just say that epsilon, or this noise, is just going to be normally distributed with a mean 0 and a standard deviation 1, such that what I get when I put this into my simulation is I get these x's which are different by observation, but I know the expected value, the mean of this variable with noise, is still going to be 15. And so I'm going to get the case that x bar when I use 10 observations is say not going to be exactly the same as x bar when I use 1,000 observations. Now, before I jump in and I start talking about how to set up a simulation in Stata, if you're thinking, well, my econometrics class, we don't necessarily just do sample mean. we do things with regressions as well. Here's an example with a regression. So suppose that your data generating process, or the truth, is that y is alpha plus beta times x plus epsilon, where we've just got a simple regression, and your epsilon is normally distributed 0, 1. The goal here again, if we're trying to show the law of large numbers, is to show that beta hat and alpha hat almost surely converge, or converge almost surely to their true values. Or in matrix notation, beta hat converges almost surely to beta. And so in our model, what we're going to have is we're going to have alpha equals 1, beta equals 2. And what I'm going to do is I'm going to generate my data as some variable y is 1 plus 2 times x plus epsilon, where just to make it easy, I'll make x normally distributed as well. And then when I do that simulation, I can ask, as my sample size gets larger and larger, does my beta hat, does my alpha hat get closer and closer to their true values? And so hopefully this makes the law of large numbers make a little more sense. In the next video, I'm going to separately start walking you through how I make these simulations in Stata specifically. So if those would be helpful, make sure to subscribe if you haven't already. But if this video in particular was helpful, please go ahead and comment below. We'll see you next time for another case of econ struggles.